Hello, multivariable students. We're going to continue where we left off with directional derivatives and gradients. I know we talked about directional derivatives before school was canceled, but a couple of you were absent either in body or mind at some point during this lesson. And now, since I'm recording these videos, I can have visuals that I don't have to draw myself. Oops, didn't mean to spin it like that. So that I can show you instead of having to worry about drawing them. So a directional derivative allows you to find the slope of the tangent on a surface in any direction, not just with respect to one of the axes. So the formula we went over is the directional derivative is the partial derivative of f with respect to x cosine theta plus the partial derivative of with respect to y sine theta. And sometimes you'll be actually doing cosines theta and sine theta, and sometimes you can actually just plug things right in because it'll be terms of like x over r or something like that. And so what that literally means is, let's say we've got this point P and we want to figure out the slope of the tangent at that point. But if you take that point and you go up to where it is on the surface, depending on which way you draw the tangent, you're going to have a different slope. So if we drew this vector here, and it's in terms of x and y only, right? But the surface is on x, y, and z. The vector is only in terms of x and y. And we go up to the point we care about, and the tangent line is going to go in the same direction as the vector was going. So they're not going to be parallel, but if this arrow was pointing kind of, let's call that southwest for lack of a better term, then our tangent line is going to be going southwest. Now let's say I drew this vector instead, this red vector, and I go up to the same point. So now I'm going to be drawing this curve here on the surface. And that could, in fact, I actually think that is going to have a positive slope. Well, maybe not. I actually might go down. So those are going to go in those directions. Now the blue tangent and the red tangent are going to have completely different values. And so that's where gradient's going to come in a second, because that will help you determine where, in which direction you'll have the steepest slope. So maybe you're hiking up a mountain or something and you want to know the easiest path to take. So you would look at the surveying data, the topography map, for example, and figure out where the gradient is the smallest and maybe take that route. Here's what a topography map kind of looks like. So the surface area that you care about is along this like XY axis, okay? And that's what like maybe your Cartesian coordinates would be, right? So maybe if we had like this vector going out, up, you'd go up, and then you'd figure out that here's the slope of the tangent line, but you could also have this slope of the tangent line, this slope, and so on. It's never ending. So this is just kind of like a more realistic view of how directional derivatives and gradient are used. One thing I forgot to mention earlier in the video is the directional derivative, the vector, we'll just say this, u is going to give you the actual direction. So this will be cosine theta I plus sine theta j, and it must be a unit vector. Now in the previous chapters we talked about unit vectors, where you would have the unit vector is the original vector divided by its magnitude so that it's a unit vector, so that'll come into place soon. But this tells you the direction that you're going, the direction. And then f of x y will tell you what the actual surface looks like. And so you'll have a vector u and a surface f of x, y. And when you put those together, that's where you get your directional derivative. And so now we're going to take a look at an example here where we're going to find the directional derivative. Alright, so this first example, find the directional derivative of f of xy equals 4 minus x squared minus 1/4 y squared at the point 1, 2 in the direction of the unit vector cosine pi over 3i plus sine pi over 3j. Now, in multivariable calculus, u is usually reserved for the unit vector. So if you see u equals, it's safe to assume that it's the unit vector. The other way you can tell is the unit vector means it fits on the unit circle, so the radius would be 1. If you tested x squared plus y squared, you should get 1. And in this case, cosine pi over 3 squared plus sine pi over 3 squared is going to give you 1. That's another way to check that you've got a unit vector, just to make sure. In this case, it's already in terms of cosine and sine, so you don't have to do anything special for the formula. We do need to find the partial derivatives though. So I'm going to find the partial derivative of x first. So 4 is a constant, that goes away. So I have negative 2x, and then the y's are constants. And then the partial derivative of y, everything's a constant but the y part. So that's going to end up being negative 1/2 y. I've got all my partial derivatives. So now I can just plug into the formula. du equals fx cosine theta plus fy sine theta, and we're going to plug in. So f of x is negative 2x, and then cosine pi over 3 plus negative 1/2 y sine pi over 3. I went ahead and plugged in theta because I know the direction it's going right now. You could also think about it as the direction is pi over 3, whichever way you want to think about it. And now I can plug in x and y and actually evaluate what cosine of pi over 3 and sine of pi over 3 are. So negative 2 times 1 times 1/2 plus negative 1/2 times 2 times root 3 over 2. And we'll do a little bit of algebra and simplifying here. These 2's will cancel, so I'm just left with negative 1. And then we've also got some more 2's that cancel. This 2 and this 2 will cancel. So then I've got minus root 3 over 2. I'm going to write that in the same color. That will be annoying. Minus root 3 over 2. And you can leave it like that, or you can type it in your calculator if one is allowed. If we stay like this for a while, you'll be allowed. Negative 1.866. So that's the slope of the tangent line going in the direction of pi over 3 at 1, 2. This example does not give you the unit vector, but you can recall that even if it's not written in trigonometric form, the unit vector in trigonometric form is always going to be cosine theta I plus sine theta j. This will always be the unit vector in trig form because cosine squared plus sine squared equals 1, and the magnitude of a unit vector needs to be 1. So this is the unit vector always when in trig form. And if you remember that I told you x equals r cosine theta and y equals r sine theta. But when it's a unit vector, r is 1. So once you have a unit vector that's in rectangular form, x equals r cosine theta. So when in rectangular form, a unit vector will equal x equals cosine theta and y equals sine theta. You ignore the r part. So that's how you can get back and forth from cosine theta to sine theta. Now, I'm going to check to see if my vector is in unit vector form, because I need a unit vector to apply the formula. And if I do Pythagorean theorem of 3 squared plus 4 squared, I don't get 1. So I need to divide by the magnitude. So the magnitude of V is the square root of 3 squared plus 4 squared, which is 5. So to get my unit vector, I'm going to divide everything by 5. So this will be 3/5 I minus 4/5 j. Well, this is my x component and my y component of my vector. So this is going to be my cosine theta, and this is going to be my sine theta when I substitute it in to the formula at the end. The next thing I need to do is find the partial derivatives. So the partial derivative with respect to x is going to be 2x sine 2y, and the partial derivative with respect to y is going to be x squared times chain rule 2 sine, nope, not sine anymore, cosine 2y. And I can just simplify that a little bit, 2x squared cosine 2y. Looks scary, but we'll be plugging in pi over 2, so it's all going to go away anyways. And now we can use our formula. The directional derivative at 1 pi over 2 is 2x sine 2y times cosine theta plus 2x squared cosine 2y sine theta. That's all the calculus part. Now it's just substitution. So I'm going to plug in 1 for all the x's, pi over 2 for all the y's, and then I'm going to replace cosine theta with 3/5 and sine theta with 4/5. So 2 times 1 times sine of 2 pi over 2. Cosine theta is 3/5 plus 2 times 1 squared cosine of 2 pi over 2. Sine theta is 4/5, negative 4/5. And we got to simplify a little bit. 2 times 3/5 is 6 over 5. Sine of pi is 0. And then in the next one I have negative 8/5. Cosine of pi is negative 1. So this becomes positive 8/5. And we can leave it as a fraction. Something useful when doing directional derivatives is knowing the gradient. The gradient is the vector-valued function of f of xy before knowing the direction. And so it's kind of the precursor to, it's like all the possible vectors you could draw at a point, and then you assign a direction to it to get your directional derivative. So we use the upside down delta, we call that del, for the notation for gradient. It's like an operator. And it's the partial derivative of xi plus the partial derivative of yj. And so we're going to use this a lot in the rest of this chapter. It's just an easier way to find the directional derivative. And so let's do an example here. We're going to find the gradient of f of xy equals y natural log x plus xy squared at the point 1, 2. So we know the formula del f of xy equals partial derivative of x I plus partial derivative of y j. First I'm going to find these partial derivatives. So partial derivative of x is going to be y over x plus y squared, and the partial derivative of y is going to be natural log x plus 2xy. And now I'm just going to plug them in to my formula. Y over x plus y squared I plus natural log x plus 2xy j. The last thing we can do is plug in the values of x and y, 1 and 2. So this is going to be 2 over 1 plus 2 squared I plus natural log of 1 plus 2 times 1 times 2 j. So this becomes 6I, natural log of 1 is 0, plus 4j. And that's the gradient at the point 1, 2. And so now what you would have is you would have this gradient, and then you can figure out the directional derivative at any direction, and you have this starting point that you don't have to rework the whole problem every single time because you have this starting point. And so the usefulness of that is if I want to use the gradient to find a directional derivative, then I would use this formula. The gradient and the dot product with the unit vector. So that's the dot product, not times, because these are both vectors. You'll find the dot product with the unit vector. And so that unit vector could be in rectangular form or it could be in trigonometric form, but usually it'll be in trigonometric form, where you'll have the gradient dot cosine theta I plus sine theta j. That's the unit vector in trigonometric form always, and you would find the dot product. And so let's just recall what the dot product is. You'll have this partial derivative of x, I, plus partial derivative of y, j. That's one vector. I'm going to dot product that with cosine theta I plus sine theta j. So the dot product is you multiply the x terms together and you multiply the y terms together and you add them. So you end up with f of x cosine theta I, i's gone because this is a scalar, fx cosine theta plus fy sine theta. And if you remember, that is the same formula we were using before for the directional derivative. So sometimes the gradient is helpful because if you need to, maybe you're solving for the direction that meets some certain standard, then you would start with the gradient and manipulate it to solve for the direction instead of being given the direction and solving for the angle. So we're going to do a couple of application questions with this. Some useful properties of the gradient. The gradient is going to tell you the direction of the maximum increase. So you could solve for the direction there. And the magnitude is the value of the maximum increase. So remember, the gradient is a vector. So if you wanted to know which way you should go to have the maximum increase, then you would find the gradient that tells you the vector. And then you could take find the magnitude of that vector, and that will tell you the maximum rate of change. The negative gradient is going to give you the direction of the minimum increase. And so if you find the negative magnitude of the gradient, then that's going to tell you the minimum rate of change. And we'll do an example where it might make a little more sense to you. Alright, so this example has a metal plate as shown by the graph to the left, and it's an elliptical shape, and it is going to measure the temperature in degrees Celsius on the surface of a metal plate. So you can find the temperature at any given location on this plate. We want to figure out in which direction from the point 2, -3 does the temperature increase the most rapidly. So the rate of temperature increase, when is that the maximum? And so we're going to calculate that rate, and we're also going to figure out in what direction you're going. So you can kind of imagine maybe the heat source is at the center of the metal plate, and you're going to be going in that direction towards that heat source. So we're going to find the gradient which is the partial derivative of xi plus the partial derivative of yj. And so the first thing I need is to find the partial derivative of x, which is negative 8x, and the partial derivative of y is negative 2y. And now I'm going to plug that into my gradient formula. So t of xy is negative 8xi minus 2yj. Bear with me because it didn't record sound this whole time I was writing it the first time, so I'm like recording sound after the fact this time. Technical difficulties. So if it's off a little bit, I apologize. So once I found the gradient formula, I'm plugging in the value x and y into the gradient formula. So I end up with negative 16i plus 6j. That's going to tell you the direction in which the temperature is increasing the most rapidly. So you could actually probably solve for theta, and then it'd be going probably like 140 degrees, whatever. So that's the direction in which the temperature is increasing the most. Now I want to figure out the actual rate of this increase, and so I'm going to find the magnitude of this gradient vector. So we're going to find the magnitude at the point 2, negative 3. So that's the square root of negative 16 squared plus 6 squared. And when you type that into your calculator, you get 17.1 degrees Celsius per centimeter. So the temperature is increasing in the direction of negative 16.6 at a rate of 17.1 degrees per centimeter. We've covered a lot of material in this video, so you probably want to watch it like one more time if it didn't quite sink in. And I'm going to post the page of the book that you need to be working on and some practice problems to work on so that you can be a little more comfortable with this before we move on to more difficult application problems. My goal is to finish with chapter 13 hopefully this week, so that we can start doing integrals next week. So we'll go by a little fast. You're going to have a take-home test probably to work on over the weekend. So make sure you see me during office hours if you get stuck on any of these, so you can stay on top of things during the week and you don't get too far behind. Have a good day.